Hey everybody, this is going to be part one of logarithmic equations. So we're going to look at two different types of log equations today, but in general our steps are going to be, condense if there's any condensing that we can do on the left or right side. And then we're going to be solving, and I'll go into more detail here in a second. But it's important to know that there is the potential for having extraneous solutions when it comes to logarithmic equations. You're going to have an extraneous solution anytime you plug your solution into your original equation and it's trying to make you take the log of 0 or a negative number. Okay, I cannot take the log of either of those. It is not possible. So if it happens, you know that your solution is extraneous and you may end up having no solution. So the first type we're going to look at today is having a log of some base equal to another log of the same base. Very similar to our exponential equations we saw. If that's the case, then in order for these things to be actually equal to each other, then the thing inside the logs must be equal. They must match. So that allows us to simplify our equation. So let's look at one. All right, I have the log of base 5 on each side. In order for these logs to actually be equal to each other, what's inside the logs has to be equal. So we're simplifying the equation, right? Like I said, very, very similar to the exponential equations in the way that we approach those. Now we can just solve an algebra 1 equation, right? Subtract 5x from both sides. We get x equals 9. And I don't have to actually plug in 9 and check the numbers and everything like that. We are simply checking to make sure that, when I plug in 9 for x, inside the log, am I going to end up with 0 or a negative number? Okay? No, we're very clearly going to end up with a fairly large positive number here. So it checks out. Same thing here. When I plug in 9 for x, I'm going to end up with a positive number inside my log. That's all I'm checking for to make sure that this solution is good. So another one very similar, right? Log of the same base on each side. We're going to take what's inside, set them equal. Oh, forgetting my number here. Okay, again, algebra 1 equation. I'm going to add 3w to both sides. We get w equals 6. We have an issue though. Okay, if I plug in, I'm going to do it off to the side here. If I plug in 6 for w, I'm going to end up with log base 9 of negative 12. On the right side, I will also end up with log base 9 of negative 12. Now, I know it might seem like that's okay because the left side's equal to the right side. The problem is I can't calculate log base 9 of negative 12. So even though it's on both sides, it doesn't really matter because it doesn't exist, right? It's not defined. There is nothing that I can raise 9 to equal negative 12, right? Raising bases to negative exponents doesn't give me negative numbers, and that's usually what people think. Okay, there is no way to actually calculate this. So even though it looks like it works out and the left equals the right side, we can't actually do it, which means this solution of 6 is extraneous and there are no other potential solutions, so there is no solution. So here's one where we have to do a little bit of condensing. On the left side of our equation, we have two logs of the same base being added, which means we can turn it into a single log by multiplying what's inside the logs together. So the left side here is going to turn into log, keep in mind this is log base 10, of 4y plus 20. Right? I just multiplied y plus 5 times 4. That's all I did there. On the right side of my equation, I still just have log of 72. So now I can take 4y plus 20, set it equal to 72, and solve away. So I'm going to subtract 20, divide by 4. We get y equals 13. And again, we're just checking to make sure. When I plug in 13 for y, do I get a positive number inside here? Yeah, and that's the only place where we had a y. It's the only one we need to check, so I know my solution is going to work. Okay, it's a good solution. So let's talk about the second type of log equation that you're going to be seeing. Okay, Instead of having a log equal to a log, you're going to see logs equal to numbers. And anytime this happens, you're going to have to convert that logarithm into exponential form. So remember, a log is asking you a question, right? It's asking, what power does b need raised to equal m? Well, b needs raised to whatever this number is to equal m. That is the conversion we're going to do. It's going to give us an exponential equation that we can solve instead of the logarithmic equation here. So here, to convert this to log form, I'm going to do 2 to the 6th power equals x minus 4. Okay, and that is really convenient because I can calculate 2 to the 6th power in my calculator. Right? That's just 64. I add 4 to both sides, and now I'm done. Okay, that's it. I solved my equation. It's very obvious that when I plug in 68 up here, I'm going to be taking the log of a positive number, so no issues. So that is it for this video. Okay, in logarithmic equations part 2, we are going to look at how we can use logarithms to help us solve really complicated exponential equations that we couldn't solve before. So let me know if you have any questions, and have a great rest of your day.